Hey everybody, this is Nicholas. Gonna explain the dot product to you guys today. So first of all, dot product, also called the scalar product, and the reason for that is once you calculate the dot product, you end up with a scalar. So I'll explain that a little more later. Um, the definition of the dot product is u dot v. So that's two vectors, u and two vectors v. Their dot product is equal to the magnitude of u times the magnitude of v times cosine of theta, and theta is the angle between the two vectors. So I have a picture later on, and I'll help clarify that for you. So when we're taking the dot product, we assume that we have the x, the y, and the z components of both the vectors. Um, Now, if we do have the x, y, z components of the vectors, calculating the dot product is pretty straightforward. So you take the x component of the first vector and you multiply it by the x component of the second vector. Similarly, you take the y components, multiply them together, and then you add them also to the z components once you multiply them together. So dot product u dot v, definition is magnitude of u, magnitude of v times cosine angle between them. Or if you have the components, the x, y, z components of both the vectors, you can calculate the dot product like it's shown down here. And then since you're adding magnitudes together, what you end up with is a scalar. So basically, a scalar is a number. A vector has a magnitude and a direction. A scalar, just a number, so it's not a vector. So when you take the dot product, you end up with a number or a scalar. So that's why it's called a scalar product. You can think of the dot product kind of like multiplication in the sense of its properties. So with multiplication, you can take u times v, and it's equal to v times u. Same thing with the dot product. U dot v equals v dot u. Distributive property, just like multiplication, u dot the sum of v and w is equal to u dot v and u dot w. It's good to know these properties when you guys are doing your homework. It'll help speed things up. Sometimes you need to use these properties as a trick, and that's how you get your answer. So just remember, dot product, kind of like multiplication, has commutative properties and distributive properties. You might be thinking, hey, what's the point of the dot product? Well, the dot product can tell us if vectors are parallel, if vectors are perpendicular to each other, or we can use it to figure out the angle between two vectors. So first of all, let's start with parallel vectors. All right, so here's the definition of the dot product. Now, if vectors are parallel, then the angle theta between them is going to be 0. Now, cosine of 0, remember from the unit circle, cosine of 0 is 1. So basically, if two vectors are parallel, then u dot v is just going to equal the magnitude of u times the magnitude of v. So let's look at a very simple case with unit vectors. So here we have the unit vectors I, j, and k. So the magnitude of the unit vector is 1, all right? And unit vectors are parallel. Well, any vector is parallel to itself. So I dot I, we have magnitude of the first one is 1. Magnitude of I is again 1. They're parallel, so the cosine of the angle between them is 1. So we have I dot I is equal to 1. This also works for j, also works for k. If we had a vector, say, that had 2, it was instead of I, it was equal to 2i. So 2i dot 2i would be equal to 4 because they're still parallel, so the cosine term is still equal to 1, and the dot product is just equal to the magnitudes of each multiplied together. So with 2i, magnitude is 2. 2 times 2 is 4. So that's why u dot v would be 4i in that case. So next up, we're going to look at how the dot product can tell us if vectors are perpendicular to one another. So when vectors are perpendicular, that means that the angle between them is 90 degrees. Again, thinking about the unit circle, cosine of 90 is 0. So it doesn't matter what the magnitude of these vectors are because the angle will always be 90 and the cosine term will always go to 0. So that's why I dot j I dot k, j dot k, it's all equal to 0. So as long as you're taking the dot product between vectors that don't have 0 for their magnitude, if the dot product equals 0, you know these vectors are perpendicular. Lastly, if you're trying to figure out the angle between two vectors, you should always think about the dot product. So the reason for that is because if you rearrange the definition of the dot product, you can solve for theta. So basically, you just take u dot v and divide it by the magnitude of u and the magnitude of v. That's going to give you the value for theta, the angle between the two vectors. And just a refresher, if you forgot how to take the magnitude of a vector, assuming that you have the xyz components of it, as I've drawn out here, to find the magnitude of a vector u, you just multiply, or you square the x component, you square the y component, square the z component, add them all together, take the square root. That's how you find the magnitude of a vector. So now, one helpful application of the dot product, besides figuring out if vectors are perpendicular or parallel to one another, is determining how much of one vector is pointed along another vector. So to start off with, imagine we have a vector u, and we're trying to figure out how much of u is pointed in the same direction of L. So now, from physics, you guys might remember this is helpful when you're doing magnetic field calculations, trying to figure out how much of a force is passing through an area is another thing I remember doing. So this may come in handy, so I'm just going to go ahead and explain it to you guys right now. So again, we're trying to figure out how much of this vector u is in the direction of L. So to start off with, we can just look at geometry. So we can break u up into a part that's parallel to L and a part that's normal or perpendicular to L. So from geometry, this is a right triangle. We have hypotenuse, so we can use cosine to figure out the parallel component. We can use sine to figure out the normal component. And if you're having a hard time seeing that, just think cosine theta from this triangle is equal to the adjacent side divided by the hypotenuse. So cosine of theta is equal to up divided by u. And then we just multiply over u, so that we get up is equal to u times cosine theta. And that's how we figure out this step. But now I'm going to do a short little proof to show you guys how we can figure out up in vector form. So basically we start out with the dot product. This guy e hat right here, I put the little hat on top of him just to show that it's a unit vector. So e dot u, using the definition of the dot product, is just equal to the magnitude of e, magnitude of u, cosine theta. E is a unit vector, so its magnitude is 1. So it drops out in the next line of this equation. So now we have e dot u is equal to magnitude of u cosine theta. But if you remember over here from our geometry, the magnitude of up is equal to u cosine theta also. So we can just go ahead and scoot this guy over here. That's how we get this line that says magnitude of up is equal to eu. So far what we've figured out is the magnitude of this guy. But we're trying to figure out a vector that represents how much of u is along L. So to do that, all we need to do is give this magnitude up, this guy over here, we just need to give him a direction. So we've already figured out that he's going to be parallel to E. So all we have to do is take this magnitude right here and give it a direction E. So what I've done with this little proof is basically I've said, okay, we start out with a vector U and a vector L, and I try and find a vector UP, which represents how much of U is parallel to L. There's an example in your guys' textbook about a ship, like an old ship, where a sailor tries to turn this device called a capstan And basically, the sailor rotates this device in order to raise the anchor onto the ship. So if you're looking at it from the top, here's this capstan with 4 handles. And the sailor's here and pushes this way, and he can rotate this device and it helps raise the anchor. So now this is pretty simple because you have a moment and you figure out how much of the moment is pointing along the axis of rotation of the sky, and then you can figure out if the anchor is going to get raised or not. But on the other hand, if you look at it from the side, this is the capstan, these are the handles. If you're just pushing down on it, you create a moment this way, and the axis of rotation is still going through the center of the capstan. So now in the second case, you're still creating a moment about this point, but none of the moment is along the line of rotation for this capstan. So even though you're creating a moment about a point, you're not creating a moment about a line of rotation. So you're not going to be able to rotate this capstan and raise the anchor of the ship. So this is just one example of how you can apply this equation up here. And I'm sure there's more in your book, and there's probably one on your homework. But this is an example I found that I thought was kind of interesting. And basically, so if you're trying to find how much of a moment is about another line, you're going to need to use this equation. That's all I have for dot product. I hope that it helps clarify some things for you. If you have any questions, just send me an email.